Hello and welcome to General Astronomy Lecture 23, Stellar Classification and the HR Diagram. Now, if you recall from our last lecture, we discussed how color and temperature are related. Here we're going to shift our focus to how spectral types and temperature are related. Now, keep in mind that we discussed spectrum of light in our light lectures, so make sure you have covered that before you get into this stuff because we'll be talking a lot about spectra coming from stars now. So just keep that in mind as we move forward. We see an absorption line spectrum when a cool gas lies between us and a hot glowing object, as we've discussed in our light lectures. The light from the hot glowing object itself has a continuous spectrum. In the case of a star, light with a continuous spectrum is produced at low-lying levels of the star's atmosphere where the gases are hot and dense. The absorption lines are created when this light flows outward through the upper layers of the star's atmosphere. Atoms in these cooler, less dense layers absorb radiation at specific wavelengths, which depends on the specific kinds of atoms present, that being maybe hydrogen, helium, or other elements, and on whether or not the atoms are ionized. A star's spectral lines provide a second way to measure a star's surface temperature. In fact, because interstellar dust can often affect the apparent colors of stars, temperatures determined from spectral lines are generally more accurate than temperatures determined from colors alone. Stars displaying spectral lines of highly ionized elements must be fairly hot because it takes a high temperature to ionize atoms. Stars displaying spectral lines of molecules must be relatively cool because molecules break apart into individual atoms unless they are at relatively cool temperatures. The types of spectral lines present in a star's spectrum therefore provide a direct measurement of the star's surface temperature. Astronomers classify stars according to surface temperature by assigning a spectral type determined from the spectrum lines present in the star's spectrum. The hottest stars with the bluest colors are called spectral type O, followed in order of declining surface temperature by B, A, F, G, K, and M. Each spectral type is subdivided into numbered subcategories such as B0, B1, and so on through B9. The larger the number, the cooler the star. For example, the Sun is designated as a spectral type G2, which means it is slightly hotter than a G3 star but cooler than a G1. The traditional mnemonic for remembering this sequence, O, B, A, F, G, K, M, is O, be a fine girl or guy, kiss me. So it's just a way to memorize it. Now this is very important. You're going to see this classification showing up a lot through the rest of our class. So again, make sure you try to understand this classification, where O-type stars are the hottest and the more blue, and down the spectrum, M is typically the reddest and the coolest. And the numbers in between don't matter a lot, but you will see them coming up again and again. So keep in mind that each category of these letters has its own number associated with it too. So this table here summarizes a lot of different properties based on these spectral types. So here you see the spectral types again, O, B, A, F, G, K, M on the left. And it gives you an example star of such a star that's in that classification category. And then it shows you the ranges of temperatures, what kind of features you might see in the spectrum, and then its brightest wavelength, and hence what its color would likely be. And you can actually see an actual spectrum of stars of these types. So notice when it's a cool star, remember we said that cool stars probably show lots of molecules because it's cool enough that they don't break apart. And that's what you're seeing here. You see lots of these darker bands on the right showing molecules. So this is just a useful table to come back to for reference. Again, like with every table, I'm not going to sit here and go through everything, but it's a great reference for you if you ever need to find some general information about these different spectral types. And again, just notice the main trend here that as you go from M to O, you're going from cooler to hotter stars, and also from red to blue stars. Now, recall that this figure here shows representative spectra of several spectral types. So we have the spectral types again on the right now, O, B, A, F, G, K, M, with the numbers too. The strengths of the spectral lines change gradually from one spectral type to the next. Stars displaying spectral lines of highly ionized elements must be fairly hot because it takes a high temperature to ionize them. And again, we've mentioned this already, but stars displaying spectral lines of molecules must be relatively cool because molecules break apart into individual atoms. So I'm saying this again because it's important now that we have this image up. The range of surface temperatures for stars is much narrower than the range of luminosities. The coolest stars of spectral type M have temperatures as low as 3,000 degrees Kelvin, whereas the hottest of spectral type O have temperatures of about 40,000 degrees Kelvin. Cool red stars, by the way, as we learned again last time, are much more common than hot blue stars. So this is just another great reference. It shows you a graphical representation of these different spectral types, their temperatures, and what kind of elements or molecules you might find in such a spectrum. And notice that it gradually changes from one to the next. So again, I'm not going to spend a lot of time going through this. Just know that it's really important. And if you want to learn more about it, you can do that outside of the class. Just look up about spectral types. It's a huge branch of astronomy. And again, notice that for the hottest stars, you see really strong bands of different types of hydrogen. So these are ionized gases. And again, you need really hot temperatures for these gases to show up. Whereas again, for the cool temperatures, you have lots of molecules like titanium oxide and things like that. So just some important properties to keep in mind. Now, I'm going to take this pretty much the same exact graph or table that you see here, and we're going to put it into a graph. So what I'm going to show you on this next slide looks very confusing, but it's pretty much the exact same thing. So let's see if we can try to explain this. This graph shows similar results to that of the previous slide. Here, each curve is in this graph peaks at the stellar surface temperature for which chemicals absorption lines are the strongest. Notice how the Balmer lines of hydrogen, that is hydrogen alpha, where is this? Hydrogen alpha, hydrogen beta, gamma, and delta are strongest for hot stars of spectral class A. So you have hydrogen here, and they're strongest for spectral type A. While absorption lines due to calcium, that is Ca, which is over here, is strongest in cooler K and M stars. The spectral type M also has broad dark bands caused by molecules of titanium oxide, which you see here as TiO, which can only exist at relatively low temperatures. When the effects of temperature are accounted for, astronomers find that all stars have essentially the same chemical composition. So we can state the results as a general rule. By mass, almost all stars are about 3/4 hydrogen, 1/4 helium, and 1% or less metals. Our Sun is no exception. It is about 75% hydrogen, with the remainder consisting mostly of helium and about 1.7% heavier elements. While the composition of most stars is similar, their size and temperature can be quite different. So this again is just a graph showing you'll see hydrogen lines for A-type stars. So let's go back and look at that. Do we see that happening? Well, here's an A-type star, and look, you have very strong hydrogen lines. And if you look for M-type stars, you see a strong titanium oxide. So you go back, here's titanium oxide showing up in the M-type stars. In fact, you see some more down here. So it's just another way to view this, these spectra. So these are basically the same things, just shown different ways. So we mentioned that, okay, although compositions are the same, well, temperature and size varies greatly. So let's dig into that a little bit before we put it all together. To determine the size of a star, astronomers combine information about its luminosity, which you can determine from its distance and apparent brightness, and its surface temperature, using the following formula. L is equal to 4 pi r squared sigma t to the fourth, where L is the luminosity in watts, r is the star's radius in meters, sigma is just a number, it's a constant, you don't have to even memorize it, or anything like that, it's just a number that you plug in, and T is of course the surface temperature. Although this equation is a little bit longer than most, it's still quite simple. It's basically just saying that we can figure out the size of the star, say the radius, if we just know its luminosity and its temperature, that's all. So this equation says that a relatively cool star, that is a low surface temperature T, so if you have a small number for T here, well, it can nonetheless be very luminous if it has a large enough radius, right? So just because it's a cold star doesn't mean it's going to have a low luminosity. You can have a cool star, but have a really big radius here to overcome that. And so that means you can still have a considerate luminosity, or considerable luminosity. And of course the opposite is true, so alternatively, a relatively hot star, which means a large temperature T here, can have a very low luminosity if the star happens to be very small, so a small r here. So we can express the idea behind these calculations in terms of the following general rules, and these are important. First, we can determine the radius of a star from its luminosity and surface temperature. Second, for a given luminosity, the greater the temperature, the smaller the radius must be. For a given surface temperature, the greater the luminosity, the larger the radius. So these things are very important, so be careful. It is another equation, and I know a lot of people don't like to have the mathematics injected into these things, but there's some equations that I just can't ignore in our course. So just be careful, do your best to understand this and follow along with it. So here we have a summary of how astronomers determine the properties of relatively nearby stars. Purple boxes in this case are measurements that need to be made, blue denotes calculations, and green shows the inferred properties of the stars. So this is just a flowchart showing you how you might determine some property of a star. So maybe we want to figure out what the composition of some random star is. Well, if we want to get the chemical composition, we just need to look at its spectrum. But let's make it more complicated. Let's just say we want to know, let's say we want to know the luminosity of the star. Well, here's the luminosity. Well, we get the luminosity from this equation. But to do that, we need to know both the distance, d, over here, and the apparent brightness. So you have to figure out the distance first and the apparent brightness before you can together use them to get the luminosity. So this just shows you a nice little flowchart on how to get from one thing to the next. I think it's a great way to summarize our results. And in fact, you'll see this come back at the end of this lecture with a few more parts to it as we learn more. Now we get to the most important thing in quite some time. To me, this is the most important diagram that we have in astronomy, but that's just because, I might have a personal bias because I love stellar astronomy and studying the lives of stars. This is what we call the HR diagram, or Hertzsprung-Russell diagram. You might get sick of these because we're going to see them a lot, and you're going to have lots of questions and problems dealing with these things if you're in my class. But it's so important because it basically takes every property of a star and then somehow manages to put it all on the same graph, and somehow without it being incredibly confusing as well. So we're going to spend most of the rest of this lecture now just discussing these diagrams and seeing how they work and why they're so important. We have seen that stars come in a wide variety of luminosities, surface temperatures, sizes, and masses. But are these characteristics randomly distributed among the stars, or can we find patterns that might tell us something about stellar lives? The key that finally unlocked the secrets of stars was the development of an appropriate classification system. Danish astronomer Enjar Hertzsprung and American astronomer Henry Norris Russell recognized relationships between these properties in the first decade of the 20th century. Building on the work of Andy Jumpkannon and others, Hertzsprung and Russell independently decided to make graphs of stellar properties by plotting their luminosities on one axis and spectral types on the other. These graphs revealed previously unsuspected patterns among the properties of stars and ultimately unlocked the secrets of stellar life cycles. Graphs of the type made by Hertzsprung and Russell are now called Hertzsprung-Russell diagrams, or HR diagrams. These diagrams quickly became one of the most important tools in astronomical research, and they remain central to the study of stars today. The horizontal axis, so take a look at the graph on the right, the horizontal axis represents stellar surface temperature and/or spectral type. Note that the two come hand in hand, so cool stars are M-type stars, hot stars are O-type stars. So the x-axis here represents temperature and spectral type. Temperature decreases from left to right because Hertzsprung and Russell based their diagrams on the spectral sequence OBAF-GKM. The vertical axis in this case represents stellar luminosity and/or absolute magnitude. Stellar luminosities span a wide range, so we keep the graph compact by making each tick mark represent a luminosity 10 times as large as that of the prior tick mark. Each location on the diagram represents a unique combination of spectral type and luminosity. For example, the dot representing the sun corresponds to the sun's spectral type, G2, so if you follow it down, it appears as a G2 star, and its luminosity is 1 times that of the sun. So if we put this dot here, we immediately know, even if it's not the sun, we know it has the same brightness of the sun and the same spectral type as the sun. So now we can start to plot other stars on here and see what happens. Because luminosity increases upward on the diagram and surface temperature increases leftward, stars near the upper left are hot and luminous, and so on and so forth. Alright, so we're going to start to piece together what a full Hertzsprung-Russell diagram looks like. This is not the whole thing, I'm just showing you it piece by piece. In fact, you can even see like a little arrow down here because I've cut this into pieces. So we're going to slowly put this thing together. Because I figure that if I give you the whole thing at once, it might be a little overbearing. So we're going to start just piece by piece. So this band here that you see stretching diagonally, it happens to include about 90% of all of the stars in the night sky. This band, called the main sequence, extends from the hot, luminous blue stars in the upper left corner of the diagram to the cool, dim red stars in the lower right corner. A star whose properties place it in this region of an HR diagram is therefore known as a main sequence star, something you're going to hear a lot. Main sequence stars are defined by gaining their energy through conversion of hydrogen to helium in their cores. In other words, if there's thermonuclear fusion in the core, it is a main sequence star. That is hydrogen to helium in the core. So these are our main sequence stars. That is the first portion, but there's more. The upper right side of the HR diagram shows a second major grouping of data points. Stars represented by these points are both luminous and cool, right? So they're pretty bright and luminous because they're up here toward the top, but they're relatively cool, K and M type stars. From the Stefan Boltzmann law, we know that a cool star radiates much less light per unit surface area than a hot star. In order for these stars to be as luminous as they are, they must be huge, and so we call them giants. Giants are about 10 to 100 times larger than the sun. Most giant stars are about 100 to 1,000 times more luminous than the sun and have surface temperatures of about 3,000 to 6,000 degrees Kelvin. Cooler members of this class of stars, those with temperatures of about 3,000 to 4,000 degrees Kelvin, are often called red giants because they appear reddish in color. So we have giants as the main category, but typically we call them red giants if they happen to be toward the right a little bit more. Well, that's the second category. There's still more. Next are the supergiants. A few rare stars in the night sky are considerably brighter and bigger than typical red giants, with radii up to 1,000 times that of the sun. Appropriately enough, these superluminous stars are called supergiants. Together, giants and supergiants make up only about 1% of stars in the night sky, or in the sky in general. So it just so happens that these bigger stars happen to be much more rare, and we'll get to that more soon. We still have one main category to look at, and that is the white dwarfs. The remaining 9% of stars in the HR diagram form a distinct grouping of data points toward the lower left corner. Although these stars are very hot, their luminosities are quite low, and hence they must be very small. In fact, most of them are roughly Earth-sized. They are appropriately called white dwarfs. As we will soon learn, no thermonuclear reactions take place within white dwarf stars. Rather, like embers left over from a fire, they are still glowing remnants of what were once giant stars. So what I'm showing you here is actually surprisingly important, and it might not seem like it right now, but I basically just stepped through the entire life of a star with you. Stars begin on the main sequence, they turn into giants or supergiants, and then they become white dwarfs. These are all things we'll see very soon. So here is, my goodness, a full HR diagram with even more information than I've showed you. This is, to me, one of the most beautiful things I've seen. And it sounds crazy because it's just a graph and a lot of people don't really care. But there's so many things on this graph with so much information that it's really hard to believe. So the existence of fundamentally different types of stars is the first important lesson to come from the HR diagram. In later lectures, we will find that these different types represent various stages in the lives of stars, as I got ahead of myself and just mentioned. For example, stars can move through the HR diagram as they leave the main sequence and become red giants. We will use the HR diagram as an essential tool for understanding how stars evolve. And again, you're going to see this thing pretty much through the rest of our course now. The HR diagram also provides direct information about stellar radii, because a star's luminosity depends on both its surface temperature and its radius. If two stars have the same surface temperature, one can be more luminous than the other only if it is larger in size. Stellar radii therefore must increase as we go from the high temperature, low luminosity corner in the lower left to the low temperature, high luminosity corner in the upper right. So these diagonal lines are showing you the radius of stars. So radius increases as you move from bottom left to top right, which makes sense. You're going from dwarfs up to giants and supergiants. All right, let's do a quick concept check. Betelgeuse and Barnard star, which are both pointed to here in the diagram with orange arrows, are both in the red portion of the HR diagram. What can you deduce about their relative sizes? So they're both in the red portion, right? But one is much more luminous than the other. So what can you say about their sizes? Take a moment to think about it and pause the video and return when you're ready. Well, they are the same color, the same spectral type, but Betelgeuse is much more luminous. So if they're the same temperature, but one is far more luminous, that means it must be bigger. And because of what we saw in the previous slide, we know radius increases as you move toward the top right. So not only because we know it has to be bigger because of its luminosity, but we also know that, radius increases as you move up and right. So what can we say about their relative sizes? Well, Betelgeuse is much more luminous than Barnard star. Since they have the same temperature, Betelgeuse must be much larger so that it can emit that bigger luminosity. Speaking of luminosities, there is something in addition to spectral types that is important in classifying stars, and that is a luminosity class. In addition to the four major groups that we've just listed, that is the main sequence stars, giants, supergiants, and white dwarfs, some stars fall into in-between categories. For more precise work, astronomers therefore assign each star to a luminosity class, designated with a Roman numeral from I to V. The luminosity class describes the region of the HR diagram in which the star falls. Thus, despite the name, a star's luminosity class is more closely related to its size than to its luminosity. The basic luminosity classes are 1 for supergiants, 3 for giants, and 5 for main sequence stars. Luminosity classes 2 and 4 are intermediate to the others. For example, luminosity class 4 represents stars with radii larger than those of main sequence stars, but not quite large enough for them to qualify as giants. So we call them subgiants. So not only do we have a spectral type now for every single star, but we also have a luminosity class. So I think I'll get into this in just a second. Yeah, I will. So I'll wait for the next slide. So now we have a complete way to classify stars. We can describe two different ways of categorizing them. First, a star's spectral type, designated by one of the letters O, B, A, F, G, K, M, tells us about the surface temperature and color. Again, O-type are the hottest and bluest, whereas M-types are the coolest and reddest. But we also have now the star's luminosity class, designated by Roman numerals, which is based on its luminosity and also tells us about the star's radius. Luminosity class 1 stars have the largest radius, with radii decreasing as you go down to luminosity class 5. We use both spectral type and luminosity class to fully classify a star. For example, the complete classification of our sun is G2V. G2 is the spectral type, which means that it's yellowish white in color. So here we are, here's our sun. It's a spectral type G2, it's yellowish white in color. And the luminosity class, here it is, it's along the V class, means that it is a main sequence star in that it's fusing hydrogen into helium in its core. So it also tells us about that. So that is our complete classification, not just G2, not just V, but G2V. And let's do a couple more examples. We can actually go back for a second here. Betelgeuse is an M2 star, right? So here's M, here's Betelgeuse, it's an M2 star, making it a red supergiant. Proxima Centauri happens to be a M5V star. Similar in color and surface temperature to Betelgeuse, but far dimmer because of its much smaller size. Similarly, a description of Aldebaran, is that on here? Yeah, here's Aldebaran right here, is a K5 3 star. So it's K5, so here we are in the middle of the Ks, and it's a 3 star. So let's go to our luminosity class. That means it's a giant. So in this case, we have an orange giant star. So it tells us that it's a giant with a luminosity of around 370 luminosities of the sun and a surface temperature of about 4,000 degrees. So you're going to need some practice with those, I'm sure. It took me a while to learn all these classification schemes and look at these graphs to make any kind of detailed discussion based on them. But, it's really important. So your book, if you have it, will help you explain these things a little bit more. But, of course, if you ever have questions, let me know. So this can now take us to spectroscopic parallax. So I told you we'll see this flowchart again. Well, here it is. A star's spectral type and luminosity class, combined with the information on the HR diagram, enable astronomers to estimate the star's distance from Earth. This method for determining distance, in which the luminosity of a star is found using spectroscopy, is called spectroscopic parallax. Spectroscopic parallax is an incredibly powerful technique. No matter how remote a star is, this technique allows astronomers to determine its distance, provided only that its spectrum and apparent brightness can be measured, and both of those are pretty easy to get, relatively speaking. If a star is too far away, its parallax angle is too small to allow a direct determination of its distance. This flowchart shows how astronomers deduce the properties of such a distant star. Note that the HR diagram plays a central role in determining a star's luminosity from its spectral type and luminosity class. So here's a new updated flowchart with lots of different properties now. So if we did want to find the distance to the star, we have to measure two things, the apparent brightness and its spectrum. From there, it's just determining properties to get us there. So we plug in our brightness B, and we can use our spectrum to get the luminosity class based on the HR diagram to pull out a luminosity and plug in. So then we can solve for the distance. So there's a lot of things now that are connected and going on, and there's lots of things that could be getting confusing. In fact, my words are confused because I'm getting excited about this stuff. I really love talking about this. So this is a great flowchart and a way for you to help reference. Maybe, I don't know if it'll happen, but if I ever gave you a problem that said, well, find the distance of this star. Well, now you have a way to kind of find it. That might be easier than going through the entire lecture again. So keep that in mind. Let's do a concept check. So how does a K5V star compare to a K52 star in terms of temperature, luminosity, and radius? So take a few moments to pause the video and think about this and return when you are ready. All right. Well, main sequence stars are luminosity class V, whereas luminosity class 2 stars are giants. So right away, just because one is a V and one is a 2, we know that one's a main sequence and the other is a giant. In this instance, we know that the two stars have the same temperature because they're both K5, right? K5 is the same as saying what the temperature is. So they do have the same temperature, so that crosses out our temperature question. What about luminosity? Well, luminosity class 2 is a star that has a bigger radius because we're moving to the upper right and a greater luminosity than the main sequence star. So the K5 tells us that the temperatures are the same, but the V versus the 2 tells us that the K52 star is both larger and more luminous. So these kinds of questions are incredibly important, and you'll get them if you're in my class again. Quite sure of it. All right, let's look at one more property of the stars before we finish our lecture on the nature of stars and then go into the lives of these stars. Well, we've talked about a lot of different properties of stars, but we've been leaving one out for a pretty good reason. We now know something about the sizes, temperatures, and luminosities of stars. To complete our picture of the physical properties of stars, we need to know their masses. Mass is generally more difficult to measure than surface temperature or luminosity. Fortunately for astronomers, about half of all of the visible stars in the night sky are not isolated individuals. Instead, they are multiple star systems, in which two or more stars orbit each other. By carefully observing the motions of these stars, astronomers can glean important information about their masses. Binary stars, or binaries, are pairs of stars that actually orbit each other. They orbit each other because of their mutual gravitational attraction, and their orbital motions obey Kepler's third law as formulated by Newton. This law can be written as follows. The mass of one star plus the mass of the other together equals a cubed over p squared. Now, if you remember, way back when we talked about Kepler's law, we saw the equation p squared is equal to a cubed. These are very much related. So M1 and M2 again are the masses of the two stars in solar masses. A is the semi-major axis of one of the stars' orbit around the other in astronomical units, and P is the orbital period in years. In other words, in order to figure out the mass of the system, all we need to know is the orbital period and the distance separating the two stars. So that's very important. But figuring out the masses of each one individually is a bit more tough. So for main sequence stars, there is a direct correlation between mass and luminosity. And this is, again, very, very important. The more massive a main sequence star, the more luminous it is. The figure here depicts this mass-luminosity relationship as a graph. The greater the mass of a main sequence star, the greater its luminosity, its temperature, and its radius. So basically, mass governs everything. So just because we have a bigger mass, we have something that's more luminous, it has a higher temperature, and it has more in size. And this is a great relationship. So everything is related, and it's so important. And in fact, we're going to get to one more thing, and I'm going to go back several slides to show this. Mass also determines the age of a star, and you're going to hear about this a lot soon. But you'll notice in this giant graph, it also shows the lifetime in green. And notice that as you go toward more massive stars on the main sequence, the age is getting lower and lower. So the more massive the star, the shorter its lifetime. So mass governs all of these properties, and we'll start to learn about how this comes to be. So I'll leave you then in this lecture with a summary slide here. My goodness, I'm not going to read all of this, but it's a summary of everything we basically just talked about. I really do recommend reading through it and referencing it if you need it. So this was our lecture on the nature of stars and then how to classify them. So there's a lot of important information here again, and a lot of it is interconnected. So be careful as you work through this stuff. And as always, ask questions if you need it. Even if you're not in my class, I absolutely welcome you to leave some comments or to message me directly if you have questions or comments about the videos. So as always, thanks for watching. And now we get to talk about the lives of stars. And this is my favorite part of the course. So I can't wait to show you. Take care, guys.